Hi all, I am K. Surya working as Assistant Professor in the Department of ECE at SNS College of Technology. In this video, let us see about measurement of temperature using thermistor. So before going to how the measurement is done, we need to know what is thermistor. So thermistors are resistors whose resistance varies significantly with temperature, making them useful for temperature measurement. They are semiconductor devices with a high negative temperature coefficient, meaning their resistance decreases as temperature increases. This property allows for accurate temperature sensing, especially in low temperature ranges. So, some of the characteristics of thermistors are resistance change, where the thermistors exhibit a large change in resistance for a small change in temperature. Next one is nonlinear relationship. The relationship between the resistance and temperature is nonlinear, typically following exponential curve. And finally is the negative temperature coefficient, meaning the resistance decreases with increasing temperature. So the temperature can be measured using thermistors in three types of configuration. First one is using a simple circuit where a thermistor can be connected in a simple circuit with a voltage source and an ammeter. Changes in temperature will cause a change in resistance, which can be measured as a change in current as shown in the diagram below. Next one is the Wheatstone bridge network, where it consists of four resistors with the thermistor forming one arm of the bridge. The bridge is balanced when the ratio of the resistances in the two arms is equal. Changes in temperature cause the thermistor's resistance to change, unbalancing the bridge and producing an output voltage that is proportional to the temperature change. And finally is the voltage divider circuit, which consists of a thermistor and a fixed resistor connected in series. The output voltage of the voltage divider is proportional to the resistance of the thermistor, which varies with temperature. There are equations which represents the resistance temperature relationship as shown here. So RT is equal to R naught into e power beta into 1 by T minus 1 by T naught, where RT represents the resistance at the temperature T in Kelvin, and R naught represents the resistance of the reference temperature T naught. Usually it will be from 25 degrees Celsius, or in terms of Kelvin it is 298. Beta is a material constant which is provided by the manufacturer. Another important equation which represents the resistance temperature relationship is the Steinhardt equation, which is given by 1 by T is equal to A plus B into ln of RT plus C into ln of RT the whole cube. There are two types of thermistors: negative temperature coefficient thermistors and positive temperature coefficient thermistors. Negative temperature coefficient thermistors exhibit a decrease in the resistance as temperature increases. They are the most common type of thermistor and are widely used in temperature sensing and control applications. Next one is the positive temperature coefficient thermistors, where it exhibits an increase in the resistance as temperature increases. They are often used as overcurrent protection devices and in self-regulating heaters. Some of the advantages and disadvantages are as follows. The advantages are the thermistors offer high sensitivity to temperature changes compared to other temperature sensors like thermocouples or RTDs. Thermistors are typically small in size, making them suitable for applications where space is limited. And the thermistors are relatively inexpensive compared to other temperature sensors. And it's also have a relatively fast response time, allowing them to quickly detect the changes in the temperature. Some of the disadvantages are the resistance temperature relationship is non-linear, requiring linearization techniques for accurate temperature measurement. Thermistors typically have a limited temperature range compared to other temperature sensors, and they can experience self-heating due to the current flowing through them, which can affect the accuracy of temperature measurements. Thermistors can be fragile and susceptible to damage from mechanical stress or high temperatures. Next one is signal conditioning. So the output signal from a thermistor circuit often requires signal conditioning to improve its accuracy and usability. So common signal conditioning techniques are linearization, which is due to the nonlinear resistance temperature relationship. Linearization techniques are often employed to improve the accuracy of the temperature measurements. The output signal from the thermistor circuit may be small, and it requires amplification to improve its signal to noise ratio. And in order to avoid the noise and interference present in the output signal, filtering techniques can be used to remove them. And finally, is the cold junction compensation, which is not applicable in the same way as thermocouples. It's important to consider the reference temperature of the thermistor and compensate for any variations in the ambient temperature of the measurement circuit. Some of the practical considerations which need to be considered are self-heating. So minimizing the self-heating by limiting the current flow through the thermistor is necessary, and also calibrating the thermistor circuit to ensure accurate temperature measurements are needed here. And also we have to mount the thermistor properly to ensure good thermal contact with the object being measured. You have to use appropriate wiring techniques to minimize the noise and interference. And also we have to protect the thermistor from harsh environmental conditions such as moisture and corrosive chemicals. So let us take up some assessment questions. Thermistors typically have a dash, as the answer is, as you know, it is negative temperature coefficient. A thermistor's sensitivity to temperature changes is always high. How does a thermistor resistance change with temperature in a negative temperature coefficient thermistor? As we know that the temperature decreases with increase in resistance, or the temperature increases with decrease in resistance in an exponential manner. So the answer is it decreases exponentially with temperature. Thank you for watching this video.